Now we will move into the new chapter, that is linear differential equation of second order. See, the form of differential, the standard form of differential equation of second order will be like, it will be d square y by dx square plus px dy by dx qxy equal to rx, where p, q, r are either constant, it will be either constant or function of x alone. They will be either constant or function of x alone. I write this as y double dash py dash qy equal to r. Alright, so this will be the standard form. Now here I'll discuss with you two methods. One will be finding complete solution. One method will involve finding complete solution when one of the integral belonging to complementary function is known. Since it is a differential equation of second order, there will be two integrals in the complementary function. So if one is known, we will see how to find the complete solution. The second will involve the variation of parameter. So let's start first one, right? Let's see the first one, how to find the first one. Suppose you know one of the integral. So your CF will be of the form something like, say, C1 f1x plus C2 f2x. f1x and f2x are your integrals belonging to a complementary function. So let we know one of the integral. Let's suppose let ux can be f1x or f2x be one of the integral belonging to the complementary function. One of the integral belonging to the complementary function. Let ux be one of the integral belonging to complementary function, and let's suppose a complete solution say I call it 1 to 1 is given by y equal to uv, where uv is the function, v is the function which we have to know. One of the integral is known, so we have to find v such that y is the complete solution. Y equal to uv is the complete solution. So we have to find v first, right? So the first derivative is going to be, it is going to be u dash v uv dash, right? The second derivative is going to be plus v double dash. So if I put everything over here, y double dash py dash qy equal to r. So if I put everything over here, this will become uv double dash plus p, this is u dash v uv dash r. So that becomes I can write this as u, if I take u common, this will be v double dash plus I can write, I collect the terms containing v first. So this will be p, and you have u dash over here, or let me rub this. This is the figure p plus 2 by u dash plus v. I have clubbed these two. So v dash, right? So this is v dash plus v into, let me club all these things, u double dash, pu dash, and q equals to this. So this factor is going to be 0 since your u is integral belonging to complementary functions. So this would be equal to, this must satisfy this equation, right? This must satisfy this equation. Since your u is integral belonging to complementary function, so this must satisfy y double dash plus py dash plus qy equal to 0, making r equal to 0. So in this case, this will turn out to be 0, right? So your differential equation now becomes d square v by dx square p plus du by dx, and that is dv by dx equals to r upon u. So this is your differential equation, right? And if I choose dv by dx as the q, then this differential equation turn out to be dq by dx plus p q equals to r upon u. So this becomes a linear differential equation of first order, and we'll solve this linear differential equation of first order, and then we can find q, and from q I can find v, and then y equal to u. We will do the complete solution. So we must remember this part, right, where q is dv by dx, Now I'll give you some hint to know what can be one of the integral belonging to the complementary functions, right? What can be the integral belonging to one of the integral belonging to the complementary functions? So we can have some hint in I can write some hint for you. See, the integral belonging to complementary functions must satisfy this equation, right? Must satisfy this equation. So if suppose you want that e to the power ax is one of the integral belonging to a complementary function, it means if e to the power ax is one of the integral belonging to complementary function, then if I put it over here, this becomes a square e to the power ax plus pa e to the power ax plus q e to the power ax equal to 0. It means if suppose this condition, if this condition is satisfied, it means one of the integral belonging to complementary function is eax, right? If I put a equal to 1, means if this condition is satisfied, then I can safely say that one of the integral belonging to complementary function is ex. If I put a equal to -1, then I can safely say e to the power minus x is one of the integral belonging to complementary function. If you want that u equal to x is one of the integral belonging to complementary function, for this the condition which I generate is p plus. So if this holds, then u equal to x is the one of the integral belonging to complementary function. If I put x square, it becomes 2 plus 2px. So if u equal to x square is one of the integral belonging to complementary function, then this condition must be satisfied. If in general I say, if suppose u is xm, then I can say m minus 1 is m into plus pm x. So if this is satisfied, this condition is satisfied, then u equal to xm. xm is the one of the integral belonging to complementary functions. So in this way I can check these conditions and get an idea of the complementary function, one of the integral belonging to complementary function. In most of the case you are given one of the integral belonging to complementary function, and then you are asked to find the complete solution. In that case we'll solve this equation, right, and get the v and multiply u and v